All right, we're now going to do an application to integrating factor. Tank problems or mixing problems have models that are nicely solved using the integrating factor method that we learned in the last class. All right, so here goes, and here's a problem. And when I read this problem, I'm going to draw a picture because that's what I do. So we have this tank, and it has a 600 gallon capacity. So possibly at the top here, we could have 600 gallons of this stuff. And it originally contains 400 gallons of a saltwater mixture. Okay, so we got this saltwater mixture in here, 400 gallons, and with 100 pounds of salt. Okay, so that's initially what's in this tank. Now water containing 1 pound of salt per gallon enters the tank at 4 gallons per minute. So water coming in here at 1 pound per gallon at a rate of 4 gallons per minute. And the well-stirred mixture exits the tank at 2 gallons per minute. Find the amount of salt in the tank at any time prior to when the tank overflows. All right, so we need to call that something. The amount of salt in the tank. So let's call that y. We've been used to dealing with y's in our differential equations, so let's call that y, the amount of salt in the tank. All right, so now to set up a model for this, what we're going to do is look at the rate of change of the amount of salt in the tank per time. So this is going to be a dy dt. So this is then the rate of change of salt in the tank. And the way that we're going to look at this is we're going to look at the rate of change of salt coming into the tank minus the rate of change of salt that's going out of the tank. And if you also look at these variables themselves, notice that y is in pounds and t is in minutes. And this to me is key. That when we look at what's going into the tank versus what's going out of the tank, we want to make sure that both of those things have the units of pounds divided by minutes. Okay, so notice that in the picture up here, I've got these two things next to each other. And if you multiply them, the gallons would cancel and we get pounds per minute. Boom, that's what's going into the tank. So I'm going to write that down. So this now, we've got dy dt is going to equal 4 times 1. So that was that 4 gallons per minute times 1 pound per gallon. So the gallons would cancel. Again, you'd get pounds per minute. Minus what's going out of the tank. Now this is something, again, that I just sort of memorize. Every once in a while I forget, and I'll tell you how I remember when I do forget. We need the variable y in there. So this is going to be y times the gallons per minute going out, so that's a rate going out, divided by the volume in the tank. Now, initially there's 400 gallons in the tank. There's 400 gallons in the tank, but going into the tank is 4 gallons per minute, and coming out of the tank is 2 gallons per minute, and that means that this tank is adding 2 gallons per minute. Every minute, 2 gallons is being added since there's 4 coming in, 2 going out. So the volume in this is plus 2 times whatever time value we're at. And that's how much salt water mixture would be in the tank at that time. Now this is a little complicated, and just in case I forget, I can look at the units. So the units for y is the salt, that's pounds. The units for that rate is gallons per minute. And the units for volume is gallons. And if you look at this, the gallons would cancel and we'd get pounds per minute. So the way I remember this is I always know we're looking at the out values. The out values, we have this 2. It has to do with the well-stirred mixture, so that's that volume in the tank. And the well-stirred mixture has some sort of a concentration of salt in it. And so I know that all of those things are combined, and I can kind of play with the units to figure out how I can get pounds per minute if I forget. Okay, but here it is. Here's our differential equation that models this amount of salt in the tank. So let me rewrite it again. Oops, let me use black. So dy dt is equal to 4 minus 2y over 400 plus 2t. Oh, and we also have an initial condition. We have an amount of salt in the tank at time 0. So notice if you go back up here, we have this 100 pounds. That would be the amount of salt in the tank at time 0. Okay, so there's our model. Now we haven't answered the question yet. We haven't found the amount of salt in the tank at any time. All we've done is find the model for it. All right, so now let me see if I can remember this, because I'm going to open up a new slide. Okay. All right, so that was dy dt is equal to 4 minus 2y all over 400 plus 2t, where y of 0 is equal to 100. And hopefully I wrote that down right. Okay, so now to solve this and use integrating factor, remember that the first step is to take that function with y, so this function, over to the left-hand side. So that would give us y prime plus 2y all over 400 plus 2t equals 4. Now we need to find the integrating factor. The integrating factor is e to the integral of whatever is out in front of y. So right now we've got 2 over 400 plus 2t. Now, if you want to, you can cancel all those 2's. Just make a note of that. I'm not going to, but really, it doesn't matter. You can cancel all those 2's. So integrate, we've got e to the natural log of 400 plus 2t. Now, there's initially a 2 out in front, so let's leave that there. And then we also have that 2 that's on the inside, the plus 2t. So when we integrate and use u substitution, we would end up dividing by that 2. All right, so the 2's cancel. E and natural log now undo each other, and so our integrating factor is 400 plus 2t. Okay? So now let's multiply everything in this differential equation by that. So we have y prime times 400 plus 2t equal to, the 400 plus 2t's are going to cancel in this next term. Oh gosh, I've written equals, that's not right. I want a plus sign right there. So plus the 400 plus 2t cancel. Okay, so plus 2y. Equal to 4 times 400 plus 2t. All right, backwards product rule. Y times the integrating factor, all that, prime, and then I always like double check this. Okay, so I take the derivative of y. Let me write what I'm thinking here. So take the derivative of y, boom. That stays the same, yes. Y stays the same, yes. Derivative of 400 plus 2t is 2. Boom. Okay. Ready to move on. And actually this side just stays the same. Integrate both sides. Integral and derivative undo each other. Is that right? That's right. Okay. And then integrating this guy. So I'm going to do this integral in maybe a way you wouldn't. And you can multiply by that 4 if you want to and then integrate. That's fine too. We'll get the same answer in the end of this. So 400 plus 2t, I'm going to square that, divide by 2. So I just took that whole quantity, added 1 to it and divided by that number. Now if I do that, I also need to use u substitution, in which this 2 comes into play, and so we would divide by another 2, and then we still had that 4 out in front. Kind of see why I chose to do that. And add a c. Boom, boom. Now divide by the integrating factors, so y is going to equal 400 plus 2t plus c divided by 400 plus 2t. All right, now we got to solve for c. Okay, so we had that y of 0. If I plug in 0, I get 400 plus 0 plus c over 400. And that initial condition, let's see, where is it? It's right here, right there. So y of 0 is 100. So I'm going to subtract 400. So c over 400 is equal to negative 300, and then divide or multiply by 400. So negative 3 times 4 is 12, and then I have 4 zeros. 1, 2, 3, 4. Okay, so there's my c. Plug that back in, so y is equal to 400 plus 2t minus 120,000 over 400 plus 2t. And there is the amount of salt in that tank at any time, so we can take any time value before it overflows. And notice that that was important. We were adding 2 gallons per minute to that tank, and we initially had 400 going to 600. That would take, what, 100 minutes. So this equation would be valid from t equals 0 to 100, and after that it starts overflowing, so then we would need a different model for this. All right.